Okay, so we're given an integer array nums of unique elements. They want us to return all possible subsets, also known as the power set. The solution must not contain duplicates, so no duplicates, and it can be in any order. So we can see for this input array, we basically are expected to produce a 2D array of all of the possible subarrays of this array, right? Or so it's all the possible subsets of this set, right? And order doesn't really matter. It's more about the elements that are in these sets, right? Because sets are unordered. Um, but yeah, so a couple of things about subsets. So, uh, the number of so there's a property, right, from like discrete math where the number of subsets from any set is going to be 2 to the n. So like for that example we had where we have three elements, right? 1, 2, and 3, there's going to be 8 subsets. When there's one element, so because that's 2 to the 3, 2 times 2 times 2 is 8, right? For when there's one element, right, it's just 2 to the 1, and that's just 2, right? So there's 2 elements. Um, so that always works out that way, and that's kind of important just because the time complexity here is going to be big O of 2 to the n, because we're going to solve this with like a recursive backtracking, and we're going to have a recursive call for every subset that we're generating, right? So that's going to grow exponentially like this. And then the space complexity, if you're considering the resulting like output, right, of this problem to be part of the problem space complexity, then it's going to be the same. Um, Otherwise, if you're not considering, the answer to be part of the space complexity, it's just going to be big O of n. So it'll just be linear because there's a recursive call stack um, that that's going to exist in the OS, right? So that's important. We'll exclude the answer, when I say this, and we'll just say linear space. Um, so let's go ahead and walk through just how we would build, like how do we algorithmically build all of the subsets of this set in a way where we only produce, where we only generate the unique ones. And like how do we do that, right? So we are going to start, regardless of the set we get, we're going to start with an empty set because we know the empty set is a subset of everything. So we're going to start a recursion, basically do like bottom up when we're building our subsets, right? So we're going to have we're going to be passing in just a single set of elements, and we're going to be modifying it actually in place. And this is where backtracking is useful. We don't have to create like a bunch of different arrays in memory to create all these arrays, right? You only have to save its state once to put it into the result, but otherwise we're going to keep modifying just the same set. We're going to keep adding numbers to it and removing numbers from it until we have like explored every possible option, right? So going this way, it's going to be a depth first search. Like if you just like stepped through the algorithm, it'll be a depth first search. But firstly, we're just going to add the first element, right? And then let's just build like a result over here. So we saved the state there. We added an element, and then we called recursion, right? So we'll have our next subset there. Okay, we're going to save the state. We're going to call recursion by adding the next element. Okay, let's save the state once again. And we're going to call recursion. So we're already down to that last element. And then we're going to save the state. Okay, and that's actually a leaf node, right? So there's nowhere else to go here. But we're going to do backtracking from this node, let's see. We're going to do backtracking back up to this node, right? And we're basically going to, let's see, we're going to undo what we did, right? So there's nothing to undo like at this portion or this portion. But once we have popped back up to this point in the call stack, we will, after we make this recursive call, right, to go down this way and add the 2, we'll actually remove the 2. So we'll backtrack, but and undo what we just did, right, and then actually add the next element, right, this way. So let's save the state of that one. 3, okay, and then right, this is a leaf node. There's nowhere else we can go, so we would go back up to this point, and at this point we would we've exhausted all of the iterations on this level, so we're back up here, and we would be going back up all the way up to this call, right? So this call was still in memory, and notice, right, this is n recursive calls, right? Or I think n+1, but it's on the order of n, right? So because this is a call, this is a call, this is a call, this is a call, and these all have to be saved, right? Like in the OS. So when it comes back up here, we would undo this one, go, that's the backtracking part, and then we would add the next possible element, which is the 2. So let's save that state, and then we can go down this way. So the next element there would be the 3. So we add the 3. Let's save that state. Okay, so then there's nowhere else to go this way. We're back up here, and then we would, we'd go all the way back up to this recursive call, right? Because we would want to undo that, adding that 2, and then go this way. And the last element there is the 3. So this is pretty much it. Let me save that last subset. So basically, this would have looked at each of these like one at a time, right? There's no like asynchronous work. This would have all been synchronous, and we would have basically saved the state of a single set 8 different times and then added it to this output array, right? And let me just verify. So 1, 2, 3, 4, 5, 6, 7, 8. So that checks out, being 3 input elements, right? 2 to the n. That's going to be 8. So yeah, hopefully that makes sense in terms of like how we're going to actually construct these. You could do this with pretty much any set, right? And then see how that works. But let's write the code for that. So the first thing we probably want is going to be that subset, just an empty array, right? An empty vector. So what this does is just creates a vector of integers of length 0. So there's nothing in it at first. That's what we'll use to seed our recursion. We also want a 2D vector for the output, right? We'll just call this all subsets. That will be the answer we ultimately return. So at the end of this, we can just return all subsets. Now for the recursive method, let's just go ahead and overload subsets, the method they give us. So we can write a private overload in the solution class. So that'll be void because we're going to be modifying everything in place. And the first thing we're going to need is just that input array, right? We're going to need all of our subsets, right? When it's time to save when it's time to save the subset to all subsets, right? So we also need subset. Subsets vector, let's see. And there's one more thing. We also need to pass in a integer, which is the current position we're at in the nums array. right, for looping through the remaining elements and constructing those subsets. So let's seed this method, right? So we're going to be passing in the empty subset, the empty all subsets, and let's see what else. Nums as well, even before that. And then just 0 at first, right? So starting at the 0th element, or the first element, right? 0th index. So before we do add any elements, we're just going to save the state of this subset into all subsets. So let's do all subsets dot push back, right? So we're just appending to the back of that array subset. Okay, then we're going to loop through the remaining elements, right? Starting from I. So we'll say j equals I. Well, j is less than nums.size. J plus plus. Okay, so the next thing we want to do is add the next element to our subset. So we'll add the next possible element. So to do that, we'll just say subset dot push back again, but this is just on the 1D array, the 1D, the subset. So we're adding the next element that's going to be nums j. Okay, so at this point, we would make the recursive call. So we can just say, we're modifying everything in place. So we just pass everything like this, nums, all subsets, subset, and j plus 1, just to go to the next element. Skip this one. Right, and then let's see. Right, we're obviously gonna skip this one because we just added the element at j, right? So we've got to go to the next element when we do our recursion, and then the backtracking happens. Finally, we'll pop from the back of the array to just like undo what we just did, like remove the element we just added, right? So like just to like illustrate like where that is in the code. So we would have just added this one. We call the recursion, right? But we also want to get the unique 2, right? So we would remove the 1. That's the backtracking, and then go down this path. So yeah, hopefully that makes sense. Let's run this. Let's see. So subsets, subset, all subsets. Let's see if I can find the bug. It would help if I look at the error probably. No matching member function for call to subsets. Void, let's see. Yeah, so we have 4 parameters here. There's 4 parameters here. So, right, we've got the order of our parameters wrong. So that's it. Boom. Okay, that should work. Hopefully. Okay, sweet. Hopefully this is helpful. If it is, leave a like, and I'll see you guys in the next piece.